just start. Let's start. Okay, so last time we talked about the lattice of flats of a matroid. You just look at all flats of M ordered. Oh, maybe it's because of the things given quantities. All right, by inclusion. And remember, a flat is a set where you can't add any elements without increasing the rank. So it's like a set of all points which lie on the given line or plane or whatever. Yeah, and so in particular, what I mentioned was that this whole set is a lattice, and if M is the matroid of a hyperplane arrangement, then the intersection lattice of the hyperplane arrangement is isomorphic to the lattice of flats of the corresponding matroid. And the isomorphism maps a flat to the intersection of just all orthogonal complements of elements in a given flat. Yeah, and it is for a central hyperplane arrangement. Say it again. Oh, sorry. Yes. Yeah. All right. So an example. Yeah, I guess I should give an example. So maybe A is something like this. Then you choose orthogonal vectors v1. And maybe this is v1, v2, and v3. Then the intersection lattice of A. So there's the origin. So the intersection lattice of A looks like it's kind of upside down. So the minimal element is the whole R2. And we have 1, 2, 3. I guess H1, H2, and 3. And H3, and then we have the origin on top. And the intersection lattice of M is, well, M is the matroid of the vector configuration of these normal vectors. V1, V2, and V3. And so if you look at all flats, then you get the empty set here, and then each vector individually forms a flat. 1, 2, 3, and then they together form a flat of dimension 2. So again, the connection here is that H3 is orthogonal to V3, and 0 is orthogonal to all elements in this set. You could take any two of them and still get 0, but that's why sort of it wouldn't be a bijection between if you take all possible subsets on the if you take only flats, then you get precisely all intersections of hyperplanes which are possible. All right. So now that you have for arrangements, we have the intersection lattice, which allows you to define the characteristic polynomial. And so maybe for matroids, I can define an analogous extension to matroids. And that's what I'm going to do, but the definition is going to be slightly weird, because for hyperplane arrangements, you don't allow, for example, none of these vectors are going to be 0. So hyperplanes give you only special matroids where there is no non-zero vectors and no two vectors are parallel to each other, for example. These are called simple matrices. So yeah, anyways, let me give you a definition. Let's say I have a matroid, and let's say E is some element in the ground set. And then I'm going to say that E is a loop if the corresponding vector is 0, or the edge of the graph is a loop. So what does it mean for matroids to be a loop? Not in any independent set. All right, yeah, that's actually, yeah, if E, that's actually there, if it's not in any basis or if it's not in any independent set. And actually, if it's like, if E itself is not an independent set, which is the same as saying not in any independent set, then it's a loop. And then dually is a call loop. So a call loop means for a graph that if you remove the edge, the graph becomes disconnected. And for vector configurations, it means that the corresponding vector is, well, it's not orthogonal, but all the other vectors lie in some, if you remove the vector, the rank drops down by 1. Yeah, if it's, well, not in every independent set, but in every basis. If E belongs to B for all basis B. So, yeah, loops and core loops are very useful notions, and I'm going to use them all the time, I guess. But now, let me define an extension of the characteristic polynomial for hyperplane arrangements. I m of t is given by, so it's going to be given by the same formula. You take the sum over all flats. So you take the, basically you take the Möbius function of the lattice of flats, and then take the Möbius function of f times t to the rank of f. That's the dimension of the corresponding. Well, actually, no, it's t to the rank of m minus the rank of f. So the original definition of the characteristic polynomial here would be to take the dimension of the corresponding intersection. So here the dimension would be 2, 1, and 0. And therefore, what is the dimension of this intersection of normals? It's precisely the rank of m minus the rank of your set. This thing here, rank of m minus the rank of f, is the dimension of the section of the corresponding normal vectors, if it comes from a hyperplane arrangement. If it doesn't, then this works for arbitrary matroids. And so, but this only works if M has no loops. And if M has loops, and by definition is just 0. So, and this is sort of unnatural. I have to make an if statement here in my definition. And first of all, I guess one way to explain the 0, which is sort of natural, is if M has loops, then instead of the empty set here, you get like the empty set is not a flat of my matroid anymore. If it has loops, I should add all the loops to this minimal element. That's my minimal flat. And somehow, then somehow you have to make, then you have to, I mean, this sum still makes sense. but because your minimal element is not the empty set, somehow the whole theory kind of breaks down. And so, another way to think about this is if M is a graphical matroid, then what is the characteristic polynomial? Okay, right. Yeah. So it's the chromatic polynomial. And so if your graph has a loop, this is a loop, call loop. If your graph has a loop, then it kind of makes sense for the chromatic polynomial to be 0, because there is no there is no proper colorings, because this edge creates a conflict of a vertex with itself. So yeah, for graphs, this is clearly the right thing to do. All right, but yeah, for now, let's just remember that. Yes, and I guess the claim is that if A, of course, this is a simple corollary of this result. Corollary is that if A is a central hyperplane arrangement, then the corresponding characteristic polynomial is just equal to, well, it's central and essential. Because matroids don't know about the ambient space, they only know about the hyperplane arrangement. Then the characteristic polynomial of matroid recovers the characteristic polynomial of the hyperplane arrangement. So yeah, now we can just study matroids. And what I claim is, what we're going to actually see is that for matroids, this theory of characteristic polynomials is much more beautiful. There's actually, because we allow loops and coreloops and multiplicities like parallel vectors, somehow the theory works much more beautifully. Let me talk about deletion, contraction for matroid. And we've seen this a bunch of times, so I guess it's going to be not too hard to guess what the definitions are. Let's say I give you an element of a matrix, and then I want to define deletion. And there are ways to define deletion when E is a loop, but I think the best way to represent these constructions is to, I mean, if you have a graph which has a loop, you can just delete it. But if it has a call loop, remember we're only working with connected graphs. So if a graph has a call loop, you're not allowed to remove the call loop. So if E is not a call loop, then how do you define the deletion of E from a matroid? Okay, nice. So you take all your independent sets and you remove E from each of them. It's I subset E minus E such that I belongs to the set of independent sets. And what if I want to define basis of the deletion? Same thing. Subset B of E minus E such that which are basis of your original matroid. And what is the rank of M minus E? Rank of M minus 1. Yeah, that's actually not true. Right, the rank of a matroid is the size of any basis. So so actually, I mean, this definition here means that every basis of your new matroid, M minus E, is also a basis of the original matroid. So the size of a basis should stay the same no matter what. But if, yeah, so let's so if your graph looks like this and there is a loop here, then the rank is the number of edges in a spanning tree. And so if you remove the loop, yeah. Yeah, so what you're talking about is actually contraction solution. So, because okay, let's actually see what happens for contraction. And here I'm gonna so here E is not a co-loop, and these are gonna be dual to each other. So assuming that E is not a loop, then indeed you can define independent sets of the contracted matroid as I subset E minus E, such that so what I do is, or what I want is that the union of I and E is an independent set. In other words, I take all independent sets which contain E, and I remove E from those. And what I get is independent sets of my new matroid. And the way to think of this is, you have a graph, and then you have some edge E, and if you choose an independent set, which is like a forest in your original graph, and you contract an edge, you still get a forest in a smaller graph. But the problem is that if E is this edge, and your independent set it uses these three edges, then after you contract your edge, it's no longer independent. Okay. So the only independent sets you get are those where if you add E to them, they're still independent, the original matrix. What are the bases of this matroid, by the way? Same thing. Okay. B subset E minus E such that B union E is a basis. Yeah, it's as you know, it's very easy to go between basis and independent sets. You just take maximal by inclusion elements. So in particular, the rank of M contract E is the rank of M minus 1, because you remove one element from each base. All right. So how are these two operations related? Well, they are dual. If lemma is that if E is not a co-loop of M, then you can you can just remove E, take the dual, and then what you're going to get is M contract. Wait, hold on, it does make sense. M star contract E. So deleting an element from your original matroid, so then it should not be a loop. Deleting an element from the original matroid is the same as contracting in the dual matroid. So, and you can easily see that, and matroid duality is just an operation on taking complements of bases. So clearly, if you look at these bases and then you take complements of these bases, then the corresponding operations are going to be related by taking complements. This is a very kind of simple lemma, although if you try to think of it in terms of planar graphs or vector configurations, it may look kind of tricky. But for matroids, it's actually, we already have all the tools to prove this easily. Okay, and so where am I going with this? Let me now make an observation. The observation is that a lot of quantities about matroids or vector configurations or zone-topple tilings they satisfy the deletion contraction recurrence. For example, if you have a matroid, if E, let's say E is neither a loop nor a co-loop, then what is true? If I take the number of independent sets, is it true that this is expressed or that this satisfies deletion contraction recurrence? Yes. Why yes? Okay, yeah, very nice. Right, so every independent set of M either contains E or it doesn't contain E. If it contains E, it contributes to the contraction. If it doesn't, it contributes to the deletion. Size of IM minus E plus the size of independent sets of M contracts E. And similarly for bases. For bases, same thing. And as you remember, these correspond to, this is like the number of top-dimensional tiles in any fine zone-topple tiling. This is like the number of vertices in any fine zone-topple tiling. And there's also the characteristic polynomial of any matroid you can show satisfies a different deletion contraction recurrence where you have to subtract the two polynomials, and etc. The number of regions of a hyperplane arrangement satisfies the deletion contraction recurrence. And yeah, so there's lots of these phenomena. And the question is, how do you explain these? What's the common generalization? And now I'm about to tell you what I think is a super beautiful common generalization of all these things. That generalization is called the Hot Polynomial. Okay, so here's the definition. Let's say you have a matroid. And then what I'm going to do is I'm going to associate to it a two-variable polynomial. P sub m of x and y. Just a two-variable polynomial, that's called the Tutte polynomial. And the definition is very simple, so defined by the following conditions. The first condition is that it has to satisfy the deletion contraction recurrence. P sub m of x, y So it's equal to T sub m minus e of xy plus T sub m contract e of x comma y. This is if e is neither a loop nor a coloop. Well, what about if it's a loop or a coloop? Then if it's a loop, the m of xy is just y times t sub m minus e of xy. If e is a loop. If it's a coloop, then you use x instead of y. Tm contract e of x if e is a coloop. And basically, this recurrence allows you to compute this polynomial. You say if you have a matroid, so you pick any element. If it's a loop, you do this. If it's a coloop, you do this. Otherwise, you do this. Basically, you can always express your matroid, your Tutte polynomial for matroid in terms of smaller and smaller ground sets. The ground set always decreases by inside. And the only thing I have to specify is the base case. The base case is when my matroid has a single element, right? So how many matroids on a single element can I get? Two. Which ones? Okay, right. So indeed, there is two possible matroids with a single element. So, and basically that single element is going to be either a loop or a coloop, that matroid. So T sub, if my element is a single loop of xy, is by definition equal to y. So y is responsible for loops. And T sub coloop x comma y is equal to x. And that's it. One problem with this definition is that it depends on some choices. And so it's not clear that it gives a well-defined polynomial. Do you agree, or do you? A priori, it's unclear. Like if I choose one edge and apply this recurrence step, maybe I get one polynomial. But if I choose a different edge, I may get a different polynomial. So it's not exactly clear that this is well-defined. That this procedure does not depend on the choices which we make along the way. It turns out that it actually works. Yes, I should. The theorem, which is due to Brylewski. 72 is that this is well defined, and moreover, it gives you a matroid invariant. If two matroids are isomorphic, then corresponding Tutte polynomials agree. Which is, when was the polynomial first defined? I think it was defined by Brylewski. I have to, well, there is one polynomial that's defined by Whitney, which is the same as this one. Yeah, I guess Whitney was the first one. But yeah, I have to actually, yeah, I don't. Well, I mean, so this generalizes all kinds of existing polynomials, and I'm going to talk about this. But yeah, apparently, I think this theorem is due to Brylewski, but I have to. I think the first definition was due to Whitney. I don't remember. But so let me explain in which sense is this polynomial universal. somehow I want to argue that out of all things which satisfy deletion, contraction, recurrence, this polynomial is universal. So what do I mean by that? Let's say I have a function f, which associates, let f be a function from matroids to some commutative ring. R is a commutative ring. For example, could be the ring of polynomials in two variables, integers, whatever. And let me assume that, first of all, it's an invariant. If m is isomorphic to m prime, then f of m is equal to f of m prime. And let's assume that f satisfies just an arbitrary deletion, contraction, recurrence. F of m is equal to a f of m minus e plus b f of m contract e. So here, a and b are some elements of R, and I'm assuming that e is neither a loop nor a coloop. Right. So, because in our applications here, we want the coefficients to be not necessarily +1 and +1. Right? In this definition, the coefficients are +1 and +1. So it's kind of surprising that you could, in principle, recover any two coefficients in the recurrence. And yeah, let's also assume that f of m is equal to f of loop times f of m minus e, if e is a loop, and f of m is equal to f of coloop times f of m contract e, if e is a coloop. Then, so assuming these four conditions, I claim that f has to be a specialization of the Tutte polynomial. So basically, anything that satisfies deletion, contraction, recurrence contains as much information as the Tutte polynomial, or less, can be recovered from the Tutte polynomial. So the claim is that then f of m is the following specialization. You take a, the size of e minus the rank of m, times b, the rank of m, times the Tutte polynomial of m, evaluated at f of coloop over b, and f of, so the x and y, you just plug in these elements, and that is the claim. Which you can check easily by, you know, the definition of the Tutte polynomial, and you can check that all these deletion contraction steps are actually satisfied by this expression, and the base case is satisfied as well. So it's actually, this is pretty easy to deduce, although it is a big formula. And yeah, so the functions like this are called Tutte-Grothendieck invariants, and this claims that the Tutte polynomial is the universal Tutte-Grothendieck invariant. And now I want to do a bunch of examples. So I just want to, let me try to do a bunch of examples. So what should I erase? Okay, let's say I want to apply this observation to the number of independent sets. Example, let's say f of m is the number of independent sets of m. Then can you tell me what is a and b and f of loop and f of coloop? A and B are both 1. Right? F of loop is 0. F of co-loop is 1. Yeah, actually, why is this 0? If my matroid is a loop, there are no independent sets. Well, actually, there is one, which is the empty set. So there should be actually 1. And similarly here, if it's a co-loop, you take the empty set or your set too. And so that means that f of m, the number of independent sets of m, is equal to what? Yeah, what's that formula for these parameters? Yeah, A and B are both 1, so you basically just get 2, 1. Very nice. So if you plug in x equals to 2 and y equals to 1, you recover independent sets. All right, let's do another one. F of m is the number of bases of m. What is A and B? And f of loop and f of co-loop. A equals B equals 1. F of loop, 1. There's the empty basis. But f of co-loop, also 1. Okay, nice. So the number of bases is what? The Tutte polynomial of 1, 1. All right. What if I want the characteristic polynomial? Let's say f of m is equal to the characteristic polynomial of t. And what is A and B? A is 1, B is -1, thanks. Okay, and what is f of loop? Zero. Right, because in my definition I had the special case that if m has loops, then the characteristic polynomial is 0. What is f of co-loop? We actually have to compute this one, right? So if E is my ground set, consists of a single element, and that's co-loop. 1 minus t, or yeah, actually it is t minus 1, right? So if this is a co-loop, and if I look at my lattice of flats, it's going to have the empty set, and then there's going to be E. So, and then you sum these with t to the, so the Möbius function is 1, -1. And then you sum them with, like, this is t and this is 1, because in the formula we had like t to the co-rank. Yeah, anyways, t minus 1 is the correct value for the co-loop. And therefore, the characteristic polynomial of your matroid is just, what is it? -1 to the rank of m times what? So 1 minus t should, yeah, 1 minus t 0. All right. Yeah, I'm gonna let me continue this list, because one other thing I want to mention is the important special case where my matroid is graphical. So let's say G is a connected, maybe multi-graph. So it can have parallel edges or loops. Then, and let's say my matroid is the corresponding graphical matroid. So then I claim that the following specializations are true. First of all, we know that independent sets are forests and bases are spanning trees. Like you can study Tutte polynomial for graphs independently, right? Because if you contract or remove an edge, you still stay within the class of graphs. You could define the Tutte polynomial purely for graphs without any reference to matroid. And yeah, maybe I should. Anyways, so if you plug in 2, 1, then you get the number of spanning trees, because these are the bases of the matroid. If you take Tutte polynomial of 1, 1, you get, oh, sorry, this is supposed to be forests, because these are independent sets. If you do 1, 1, you get spanning trees. If you do, but now it gets interesting, because there is more and more specializations. So if you try 1, 2, what you get is the number of connected subgraphs. Again, you're supposed to use all the vertices. Now, if you want the chromatic polynomial, then there is a formula as well. So basically, this formula here is almost the same for graphs, except that you have to multiply this guy by t. T times the Tutte polynomial 1 minus t comma 0 is plus or minus the chromatic polynomial of your graph. And why do you have to multiply by t? Well, because the graphical arrangement is not essential. We had a statement that the characteristic polynomial of the hyperplane arrangement is literally equal to this, but because that arrangement is not essential, you need an extra t front. And it just keeps going. If you go to Wikipedia, there's like many more specializations. If you plug in 2, 0, then you get the number of, and these are all meaningful combinatorially, number of acyclic orientations. Of my graph G, which, by the way, we've seen acyclic orientations before, right? What was the previous interpretation? Does anybody remember? Nice. Yeah, it's the number of regions of the graphical arrangements, and that's what you get when you plug in t equals to -1. Right. So in general, this is the characteristic polynomial of the hyperplane arrangement. So you plug in t equals to -1, you get the number of regions, which is now defined for an arbitrary matroid. This is basically the number of regions of your matroid, in a sense, although it's not clear what it means for an abstract matroid. Okay, what if you plug in 0, 2? You get the number of, also a number of orientations, but different ones. Is the number of strongly connected orientations. Right? Where strongly connected means that you can go, for any two vertices, you can go from one to the other by following the arrows. And finally, Tm of 2, 2 is just 2 to the number of edges. Which, yeah, this is a lot of information to consider. And but to me, the point is that computing the Tutte polynomial of a given graph is a very powerful thing to do. Right? You just get all this information for free by just plugging in different values of x and y. Now let's try an example. Yeah, I'm going to go backwards now. Okay. Let's say I have a graph G, which looks like this. 1, 2, 3. Complete graph on 3 edges, 3 vertices. Then let's compute the Tutte polynomial. How do I? Basically, I want to use this definition here, deletion contraction, to compute the Tutte polynomial. So let's choose some edge. Which one should I choose? 1. Okay, let's do 1. So if I remove 1 minus 1, then what I get is double edge like this. If I contract 1, oh sorry, if I remove 1, I just get this 2, 3. If I contract 1, I get this 2, 3. Now let's choose some other edge. All right. So here 2 is it a loop or a co-loop? Or neither? It's a co-loop, so I should look here. If it's a co-loop, I multiply by x. Minus 2. If it's a co-loop, I contract 2. I should contract 2 and multiply by x. I get 3. And here 2 is it a loop or a co-loop or neither? Neither. Okay, so I should apply this definition here. Let's see, if I remove 2 and minus 2, I get just a single edge. If I contract 2, then I get a single loop. And these are all base cases. So for a loop, I get y. For a co-loop, I get x. So this would be x squared, right? Because there's an extra x here. This would be x. And this would be y. In particular, my Tutte polynomial for G, yeah, let me just call it T sub m. Of xy is just x squared plus x plus y. Whoops. Oh, I'm out of time. Oh, that's bad. All right. Yeah, I'm going to continue. Oh, I'm going to continue after Thanksgiving break. That's not good, but all right. Yeah, so remember all of that, and then we're going to apply that to this in 5 days. Yeah, anyways, everybody have a good break, and I'll see you all on next Monday.